mostly we'll cover some of the programming parts for linear algebra, and there's some derivation that got mentioned in the class and will be mentioned in the class that, but professor will likely be skipped through. But I will go through it with you together, such that you understand what's going on. And for the math part, if it's too confusing, feel free to just unmute yourself and then shout out. I will explain in a more detailed way. Okay, let's go through the linear algebra. So the linear algebra parts would be most likely Numpy, because as I mentioned before, is a very powerful math libraries, especially for linear algebra in Python. So let's get started. So one note is that you will be able to find the material and also these notebooks on the websites, but there are some inferences like for this in this notebooks we will try to show image in this notebook, but those images hasn't been uploaded to the website, so it will be uploaded very soon. And once it's uploaded, you can download it and then play with it. This is just one example of. I will leave this to you to play with. It's some sklearn predefined data sets that you just play with it. But basically, it's very similar to the examples of the Zoom rental that got mentioned in the class, in the lecture. Let me see if anyone is chatting. Wait, can anyone chat in this? Okay, yes, okay, thank you. Because I didn't see it. Cool. So linear regression, well, as mentioned, it will have the form that y equals to xw, where w is is the weight for well, if it's a classification problem, then the w will be the weights for just one class. But for linear regression, this would just be a weights for every components, assuming linear model. And x has, so each row of x will be the data set, will be each data points, and row of it. So each column of it means different features of the data of this data points. And note that the offsets b is included. It's just another way to write it, rather than without this column, you write it as xw plus b, where b is commonly shared in this case. If you would want it to be general, you can have a different b's for different that's fine. For different data sets, I think. Sorry, data points. Okay, but that's not very important. It's got mentioned in the class, just a recap. Okay, we can go through the matrix. So usually matrix, well, mathematically matrix is defined by a 2D or square array or square. Well, it's just a bunch of numbers that you decided to put it in a square way. And well, this is one way to initialize it, initialize one array matrix. And this is just how you would print it. But if you are using NumPy, if you use Python and not using NumPy, you have to use this nested for loop, depending how much, how many dimensions that your NumPy array has, that you keep looping through until you get calculate like calculated results. For example, if you want to calculate, maybe comment it maybe like this. That means you want to calculate what happened if you square element-wise square this matrix. This will just, you will have to do it this way. Oh shoot. Yeah, but with Numpy, you can simply do this, which is very convenient, and also very fast because this operator is supported by Numpy, which was rewritten in C, and which is like decades times faster than this. Okay, and vectors are are one-dimension matrix if you see it that way. So, but in terms of NumPy, it was defined. So it's a 1D array. There's one thing you need to note, that sometimes we write like this is a column vector, so it's like 4 by 1. It's actually if you write it explicitly in math, notice in math, not in Python. This is 4 by 1 in math. But you can also write a row matrix, row vector in this way. So the -1 is just for automatically calculating what that dimension is. So this is just turning this equivalently in math. This is 1 by 4 vector. I guess that's it. Okay, for matrix addition, this is the part where NumPy got useful. Otherwise, you've seen this with power of 2 before. So you can just use the plus operator rather than having, let's say, this. Oh, shoot. Rather than having this nested loop. So my advice, or it's kind of a unspoken requirements, never do this sort of things in your homework 1 code, because you will, I basically can promise you that you will fuck up if you do this. You won't be able to run the experiments, or you will, but not fast enough that you can debug. Just for your experience, don't do this. I think it's maybe the 3rd time I talked about this. Okay. And the okay, I'm not so sure about NumPy, but definitely PyTorch, but never mind. So I think, yes, so for NumPy, there is also a broadcasting property of matrices. So if you do something like, sorry for, let me do some little experiments. So the problem, like the pre-requirements to use this A plus B notation thing is that they have like the same shape. As we know, like mathematically, you have to have the same shape of matrix to have a legit like plus operations. But I think you can also do things like this. Let me see. So by broadcasting, I meant if you can, by that I mean if you have y having the shape of like, because b have the and so y have the shape 1 here, but a and y has the same dimension in the second, has the same shape at the second dimension. So you can do something like this, if I don't remember correctly, hopefully. You can do this. And still, so y will be repeatedly plus at each rows. And let's see what y is. So y is 0, 1, and it was plus added to. Sorry, I should also print y. So 0 is not added, so it's added here, but nothing changed. And 1 is added here, so everything in the second column is it's added incremented by 1. So the reason I want to mention this is just one trick that you can save yourself from replicating y's into the shape of a. Let's say stacking, like you don't have to do something like y, when you're trying to calculate a plus y. There's one way that, like, if you don't know this property, you have to do something like first stacking y, 3 y's, or and then do a plus y, but that's not necessary. Array. Yeah. But like, okay.
Question for that trick.
Yes. Right. Sure.
Does y have to be like a 1 by n matrix, or is that like a vector then?
Sorry, what?
If we're just like trying to add like y to every like row of a,
Yeah.
does y have to be a vector, like a 1 by something, or can it be like a 2 by 2?
A 2 by 2? No. So you have to have one at the dimension that you want to like add it like over and over,
Okay.
and have the dimension fixed at the rest of the other dimension.
So it has to be like, there has to be a 1 somewhere,
right? Yes.
Okay.
1 is the dimension you wanted to iterate over.
Gotcha.
Yeah. Yeah. Before it fucked up because y has a wrong shape. So if I stack y, like using this reshape, it will have 3 dimensions. So I'll have like a 3-dimension thing was printed out. Yeah. So try to like, so one takeaway from this accident is that that I also want to mention is that Numpy sometimes will allows you to run a wrong code, the code that you are not meant to run, but you're still running it successfully, but it did the wrong thing, which got this bug lurking in your implementation, which will get you the wrong final answer. But your code still runs, and you're so confusing why that's happening. So my advice would be, when you do the programming thing, try to programming line by line, checking whether you have exactly the same thing you wanted to do done by Numpy, by your code, which is super important. Yeah, I think that's it. But even though I sort of warn you guys, you're still having a little bit of trouble. That's very normal. Don't worry, you'll be fine. that's why I highly recommend using PyCharm rather than, I'm not sure about VS Code. I think VS Code also support interactive like debugging, but Numpy is the one that got fully, like, lots of features integrated. So yeah, that's why I think you should use PyCharm to make sure dimension and everything is correct. And scalar matrix multiplication is just times the scalar, nothing special. Yeah, it's basically everything with like matrix. You can if you can write it in a math form, you can write it in PyCharm. Yeah, that's it. And matrix vector multiplication. So like this is just the expression you want to memorize. So dot, it's a very powerful operator. It has different interpretation depending on your inputs. I recommend you to read through the documents because sometimes it maybe did different things. For example, sorry. Here, ax would do the matrix multiplication. But if you do like xx, although like this one can be considered as a dot product between a matrix and a vector, but it just has different interpretation, like different interpretation in math, I guess, for different people. But if you do this, it would just be a dot product between x. But here, oh yeah, x is so if you want to do a dot product between two vectors, you have to be one dimension NumPy array. But here we have 2 dimension. So okay, let's go through it. Matrix multiplication would be basically the same as this one, except that A and B have to has the dimension, the second dimension of the first matrix needs to fit the first dimension of the second matrix. Yeah, just basically this line. Okay, there are some example, rank and inverse. I'll leave those to you to explore since we want to also cover some derivation. Here, there's the last thing I want to mention is this part. Be sure to use this rather than inf, because inf is inefficient and details explained here, and also examples. Because for this class, I think you will frequently use, because most of the time in this class, most of the time we have the closed form, and we'll solve it using potentially using maybe one of those 3. So be wise to choose which one to use. Okay, I guess that's it for the NumPy tutorial. Okay. Let me switch to my okay. Okay, could you guys see the, oh shoot. Okay, let me see if we can, it's not sharing or it's sharing? Wait. Okay, cool. So could you guys look at the section material available in the website? So the first part is the very typical linear algebra, some principle, something that about like null spaces, and rank. I will leave you guys to that. There's not much knowledge I can told you, like it's there. So just go checking Google type of thing. The derivation part I want to share with you, I want to go through with you is the how we calculate this argument. Cool. X, W, Y. This is the list. Sorry for the handwriting. Sorry. Least square arrow. And we want to find the W that minimizes the whole thing. And X, sorry, assuming n data points. And each dimension, has a D. Sorry, each data point has D features, including or not including offsets. That's not important for us. Like you can write it as XW plus B minus Y, but this B is not super important. It will basically follow the same proving procedure as this one. So for simplicity, I will just go through W. So X has the dimension m by D. W is D. Y is also D. The way we do this is by using calculus. So the usually, sorry, the case is not suitable for writing stuff. So using calculus, first we want to rewrite this because, well, this norm is complicated. So we want to rewrite those. Oh, and also note that there's this results. So X W minus Y is in in N. Because N by D times D by 1 minus D by 1. So this part and this part, they collapse into, oh, sorry, this is, collapse into N by 1 minus N by 1, which is N. Okay, so, okay, let's go back. We first write it in terms of transpose. These two are equivalent. Can anybody, can you guys understand why? Let me see the chat. Just curious what notes are, okay. For Vincent's question, although it's privately, it's notability. So notability. Okay. The reason why this, oh shoot, this and this are equivalent is that this one, oh sorry, I should probably use this. This one is simply, okay, let's write it this way. It's equals to, assuming A is some n-dimension vector. This is, yeah, because L2 norm without the square will have a square on the outside of this summation, but we have a square on the L2 norm. So And this is equivalent to A because like equivalent to this this thing because we'll just A transpose A is just is by definition of this transpose like transpose matrix multiplication in this case. This. So you take the value of here times this value of here, but these two are identical. And you do it many times. Okay, so let's continue. So let's first do this, like take this transpose, distribute it into this expression. We'll have W transpose times X transpose minus Y transpose. This is just some rules of for transpose, like defined or by math, if you say so. And then remember in the matrix multiplication case, A plus B or yeah, anyway, A plus B times C minus D will follow the distributive law in terms of normal math operators. So we'll have A times C, A times D. So we'll do that. W transpose X transpose times XW minus W transpose times X transpose times Y. And then similar for Y. Cool. We have this long, complicated expression for our so this is our loss. Each one of those are our loss. And we want to minimize this with respect to W, or W being the vector. So as mentioned in the lecture, we'll use calculus. So using calculus, we'll have, so this, I won't explain why this is, like the result is this, because, sorry, I think the result should be this, if I don't remember wrong. Check there's something, so just Google matrix cookbook. This is the closed form, sorry, this is the like derivative of this matrix. But I think you guys have done similar things in homework 0. Is it, or is it gonna be homework 1? That you will sort of derive by your hand why this is the case. I'm not so sure.
Can I start with a question?
Yeah, sure.
Can you explain what the W vector is again? Like what it represents?
Oh, this is the weight for each feature.
I see, thank you.
Yeah. And for this one, I think this is gonna be, so by doing this, I mean, I'm doing this operation where the dot refers to the whole expression. And Y transpose Y is a constant. and the derivative with of a constant with respect to anything is it's 0. Yeah, I will erase this. You should put -0, and okay, we can then simplify this expression. And okay, how do you do this? Now we're just going to set this derivative to be 0. Now we have this expression. We can move this to the other side. But 2 and 2 is canceled. Now we have this W. So like we can treat this. Oh shoot. We can treat this as a single matrix, and left times its inverse. So and this one will be cancel. Oh, well, not cancel, but like this 2 will be identity, which is equals W itself. So when so this expression means when W equals to this weird thing, the derivative of our loss will be 0. Oh, I guess I don't need to write this. Will be equals to 0. And since this is a convex function, it's just a linear and then square. It's the convex function, like in 2 dimension would just be something like this. So when this is when the derivative is 0, we'll reach the single what do you call it? Global minima. Sorry for this confusing. It doesn't have to be on this axis. Is everybody still, is it clear for everyone?
When you're deriving, are these just like rules that you just happen to remember?
You mean this
Yeah.
part?
Yeah.
Well, yes or no, and no, because yes, because I do memorize this this formula, but no, because they can also like they can be derived. Like there is a principal way you can derive this this formula. Any more question? Okay.
Sorry, I do have a question.
Yeah.
And this might just be like a basic derivative thing, but in the first term where you have 2x transpose xw.
Which part? This one?
Right below it.
Oh, this one.
And you have it. Yeah, you have a 2 right there.
Yeah.
And that's because you have like 2 w's.
Yeah,
right?
you have 2 W. Yes.
So it's like w squared almost, and like
right. That's the analogy you can make. Yes.
Okay, I think I did the homework wrong, but this is good to know. Thank you.
Yeah. And later there will be something called reach regression. But that's basically the loss function would just be exactly the same as before, plus a regularization term, because it will help us for dealing with something called overfitting. I'll remember from the lecture, there's a example where like they're this point. You can either have, let me use different color. You can either have this to fit those data points. You can also have a zigzag, I don't know, lines or polynomial to fit those data points. So this is definitely overfit. Because what if there's another data points that lies here, but also like drawing from the same distribution, your model will fuck up. Okay, we can go through the ridge regression, but it will be you will feel very similar to what happened before. So let's do a similar thing. First, write those in terms of transpose, just to another reason that we write this this square norm into this into the transpose is another reason, is a reason why, like, because we want to it helps us to derive this derivative formula. Okay. XW minus Y plus W transpose W. Then, okay, when we do similar things, stuff remains, which is, right. And plus this lambda W times 2 being this you can see as W squared, and then when you derive this, you will be 2W, but that's not very important. Okay, and then set it to 0. You will have, let me see, which way should I put this? So 2, so 2 can be canceled. And then move this part. So we want to have W, all the terms has W on this side, and no W on this side, such that we can like simplify, and then that's the typical way you would do calculus or algebra. And this expression seems weird, because how can you just so we want the stuff we want is that we want to take this out and write it in a form like A times W equals to this. But obviously we can't have X transpose X plus a scalar. That's not possible, but there's a way around, meaning that we can rewrite this expression. Rewrite this expression into lambda times identity times W, which is equivalent. But then this will give us lambda in a matrix form. But the meaning is the same. We will add lambda to each every single term in this matrix. Which will gives us, and then now we can take out the W. and then we do the similar multiply by left of its inverse. We'll have this as the results of our ridge regression. This is the closed form solution for ridge regression, which I think will be discussed in the next lecture. And we are almost out of time, right? Oh, there's still 5 minutes. Let me see. What else? Let's discuss. Oh, right. There's another thing very interesting derivation I want to talk about. This is the bias and variance trade-off. No, we have 10 minutes because we started later. When will homework one be out? I think it will be either tomorrow or Saturday, and you guys will have like about 2 weeks to do it, which is very reasonable amount of time. Okay. The in this bias variance trade-off, we have that very confusing expression here, given x equals to x. And we want to prove why this, why the best minimizer is this. Well, an intuitive explanation is mentioned in the lecture because this one is greater than or equal to 0. So the best one you can get is when the eta x equals to this. But we can use similar trick that we like derivation and calculus trick we used before. This will just be this is the partial. No, that's not partial. Derive with respect to let's put it this way. Let's set cx equals this. This does not change the results, but just better for notation. And now we differentiate with respect to cx. It will gives us so let me write. And we can push this into this expectation because it does not affect the result. Like there's no randomness here. The randomness comes from y or y conditional x equals to x. So we can push this derivative into this quadratic. And then do the derivation, do the differentiation. And there's a minus because here. Now we want to set this to be 0. And because both sides is like this side is 0, so like -2 can be canceled. And because of the sorry, the property is called linearity of expectation. We can break this into y conditional on x, expectation of y conditional on x minus expectation of cx conditional on x. And then we move this. I'm sorry, there's another step I skipped. And since C is Cx, or this one, is a deterministic function, like by that I meant if you plug in x, you'll deterministically get the results. So this is just Cx. There's no expectation, or you can say the expectation of some constant is the constant itself. So the Cx will be the expectation of y, x given x. And that concludes this sections. Is there any more questions? Yes. So the truth, or you can see eta x to be the true function, or the best model you can ever get. Yes. In terms of minimizing this loss. Yeah. Any more questions? Yeah. Metrics. Okay. Which, the first one or second one? So you can see this as when you differentiate with respect to W, you take out its W transpose. If it does not have a let me see. So if it does not have a, so the idea is you take out its transpose. So this was taken out. If there's no transpose, you will take out the W and then transpose this, its coefficient or whatever you call it, or the constant term of this W. Yeah, that's why you got this, because y transpose x transpose will means that you first do the transpose inside of it, which will leaves you y and x transpose, and then you flip this, you're rotating everything from left to right. So you rotate x to be the first one and y to be the second one. Yeah. Why can't I? Okay. Any more question?
Yeah, do you have a link to a reference for derivations you did in class here?
I don't think so. but I think you can Google it. Yeah, that's the answer I have. But sorry. The way you, so normally, the way you would derive it is that so you can write this into its summation form. And think about how you would derive with respect to Wi or Wk, where k equals to, it's ranging from 1 to n.